All right. Greetings, everyone. So we're going to be talking about liquid cellular automata and how we made them a bunch of scaredy cats. So a bit of background, liquid cellular automata is essentially cellular automata that are not bounded to the sort of grid space that we had seen prior. That a cellular automata are essentially able to freely move around the space, even to the point where they're able to occupy the same point in space. And so we're very interested in density classification. So the ability to essentially have the whole system converge to whatever the majority is when it's starting. So the idea is that you'll have, like say that you have 51 black agents, and then you have 49 white agents. And the idea is that you want to have the whole system become black. And so here's an example of liquid cellular automata in action. Essentially, you have all of these agents that are moving around, and you want to converge on whatever the initial sort of starting majority was, that every single agent is in that state. So a bit of so we wanted to be able to add on some extra behaviors. So the ability to teleport randomly within a radius, or teleport in the forward direction. So this would be equivalent to taking a very large step. And then also we wanted to investigate the idea of going dark. So where you stop communicating, essentially you stop being influenced by your neighbors and you stop influencing your neighbors. And that those two things would be triggered by two different things. It could either be randomly, so there would be some kind of percentage chance where essentially one of those, where that would be, one of them would be triggered, or the case where they get overwhelmed. So that's the sort of scaredy cat thing of essentially, if you have within some scalar of your network radius, if there are so many X agents within that area, that you would then trigger one of these above behaviors. So you would teleport away, or you would go dark if you were in a dense area. So the idea is that we're just looking at sort of a majority voting within this small defined radius. And the hypothesis is that teleportation should have similar performance to going dark. Essentially, the idea of that they should both come up with the same correct consensus. And so, of course, there's lots of applications for this, quantum computing, or where systems go down, or where network systems go down, and things like that. So here's an example of those running where the difference were randomly going dark versus overwhelmed going dark. And so it's sort of hard to see. We add a little border around, we change the color border to indicate when it's gone dark, so that we can see that it's not influencing other agents. And so what we found was that there was a significant performance difference between going dark and teleporting. The idea that so just this is the case where they're randomly doing it. This is the case where they're overwhelmed. So that's scaredy cat nature. And so that just them coming to the correct, the correct consensus was actually different. And the thing that we also saw, which was curious, was that we actually saw degraded performance of coming to the correct consensus from just the normal cellular automata. But the thing that we did see an improvement with was the actual time to come to consensus, whether or not that consensus was correct or not, that you could actually converge quicker if you were doing this random teleporting, and that we saw that the teleport forward and the dark were somewhat similar in the number of iterations, but then the case with the scaredy cat, where it goes dark, that it's quite terrible. That it takes a much longer time to converge, which after thinking about it, it makes sense. So essentially, the main question was, does teleportation and going dark lead to the same overall behavior? And so our conclusions was, with the parameters that we tested, that no, they that they're actually different. We see different behaviors and the time to converge, and then we also see the actual the correctness of what they converge to also being different. So yeah, thanks for your time and attention. Anybody have any questions?